Okay, so we're working on this gas variables, POGL. We started with model 1 where we were talking about okay, so in model 1 we were talking about a non-flexible container. And so we can't change the volume on a non-flexible container, right? And in model 2 here we're talking about a flexible container. I think it's important to note the two differences. Here's the main ideas. I don't know if you want to make a note on there, but it might be a good note to make. But if we've got model 1 with a non-flexible container, that means that the volume has to stay constant. Okay, so the volume will not change. Now, depending on the material the container's made of, like for example, you saw the 2-liter bottle that I had, and I put hot water into it to make hot gas inside basically when I poured it out, so the gas was really warm, right? Put the cap on it so the gas couldn't get out. And then we sat there. We did see the volume actually constrict on it. It was a non-flexible container made of plastic, but I mean, if we can make the pressure inside really low, we can make the sides cave in. We're going to be modeling that tomorrow, by the way. So what's special about flexible containers? Well, what's special about flexible containers is, well, the volume can change now, right? So we can't write that the volume is constant anymore. And what's really important is that not always, like in the process of expansion or contraction, the pressures can be different. But if the flexible containers, if the walls of the flexible containers are not moving, then that means that the internal pressure is equal to the external pressure. I think that's the main idea here. Okay? So let's see what you guys put for answers. So if we go to number 12 here, what did you guys put for materials that they could be made of that would be flexible? Rubber? Latex? Did you guys come up with anything else? I also told some people bubble gum would work. Oh, you can blow bubbles with bubble gum, right? You can make them big, small, expand, contract. We can't, yeah, we can make them contract if we take air out. All right, and then B, which is what I was just talking about. So who can tell me this answer? What is always true for the external and internal pressures? They stay the same. Is that a good way of explaining it, though? Because they can change, right? They're always equal. So the pressure internal equals the pressure external. Okay? Everybody's got that? All right, so 13, we have a table here. We got to find the independent variable, which we know is really what we call the manipulated variable. We got to know the dependent variable, and then what are the controlled variables, the variables that aren't changing, right? So let's go back and look at the actual experiments, see if we can identify these things. Big clue that we got from doing the assignment yesterday and going over it yesterday was that this tells you really what the independent variable is, because it tells you what you're doing in the model. Okay, so in this first model, we are adding more gas each time. So we start with 4 particles, and then we go to 8, and then maybe 12. I don't know what that is. But we're changing the amount of gas on purpose to see what happens. So that would be our manipulated variable. And what's our dependent variable? Is it pressure? The volume? How many people think volume? Raise your hand. Nobody thinks volume? Jerry, you think volume? What's changing as a result of adding more gas? Because that's what the dependent variable is. Okay. Is the external pressure changing? No. Internal pressure? Temperature? Okay. Amount of gas? Amount of gas is changing. We're changing it on purpose, right? So what's the other thing that's changing that we didn't change on purpose? Volume. So on our controlled variables, what didn't change? Amount of gas changed, volume changed, pressure external did not change, pressure internal did not change, and temperature. Okay. So really, on all of these, if you notice, by the way, the 5 variables that we were talking about, amount of gas, volume, external pressure, internal pressure, and temperature, all 5 of those get listed somewhere in each experiment. All right, what about experiment D? What is the manipulated variable? Temperature. You guys all agree with that? Anybody disagree with temperature? Raise your hand. You guys all agree that it's temperature. Why? Why is it temperature? Well, what does it say in experiment D? We're doing heating the gas, right? We're changing the temperature. And we can see here the temperature do change, right? What else is changing? Okay, amount of particles, if I look at that first, and amount of particles, that's not changing. Volume is changing. Okay, if temperature is our manipulated variable, then our dependent has to be what? Volume. And our controlled should be all the other ones. So amount of gas, pressure external, pressure internal. I'm going to talk more about the pressures in flexible containers tomorrow, because it's kind of a tricky concept. And experiment E. So what is the manipulated variable in experiment E? Okay. External pressure. Disagree with that? Pressure external? Does anybody disagree? What does it say we're doing on this experiment? We are reducing the external pressure. So therefore, the variable that we are messing with on purpose, that we are manipulating, is the external pressure. So Kanye, what does that make the dependent variable since you have your cell phone out and since that's on video now for parents to watch? What's the dependent variable? I told you guys if you want to volunteer, the best way to volunteer is to have your cell phone out. Guess who's answering the next question? Get that hood off. Yeah. Volume, he says. Does anybody disagree with that? Let's look at what's changing. What are our variables in this experiment? Is the gas changing? Nope. Is the volume changing? It is. Yep. Goes from 1 to 2 to 3. So that's a variable. And the other thing that's changing, external pressure. And internal pressure is changing too. Why is that? Okay, so if we're changing the external pressure, that means the internal pressure is going to get changed as well. So would it have been wrong of us to say that the manipulated variable could also be internal pressure? It would have been wrong? Or we could have said that. Right, but in a flexible container, if we reduce the external pressure, don't we also reduce the internal pressure? So that's going to make, this time, our controlled variables a little more difficult. So we know the amount of gas is not changing, and we know the temperature is not changing, but I don't think I would put the internal pressure, because the internal pressure is changing here. What's that? So it wasn't being changed by us, it was changing as a result of what we changed. Good thinking. Nice job, Josh. Little shout out on the video for you. Jade? N is a quantity, which means the amount of gas. Okay, that's just the way you see it in formulas and stuff. All right. Good. So number 14, provide a molecular level explanation for the increase in volume among the balloons in experiment C. How often and or how hard are the molecules hitting the sides of the container? So what did you put for this one, Anaya? What did you put for this one since you have your cell phone out? Can you put that away? Yeah. Turn off the game. So what did you put for this answer, number 14? Anybody want to help Anaya with 14? Experiment C, what were we doing again? Refresh my memory. We were changing the amount of gas, we were adding gas. Okay, so why would that make sense that the volume would increase? Jerry. Well, volume's the amount of space something takes up, right? What's that? Oh. Josh? So if we add more particles, it's safe to assume there's going to be more collisions, right? And if we get more collisions, makes sense that we're going to have more pressure inside, right? But wait a minute. We can't say that because the internal pressure has to equal the external pressure. So you're telling me that if we add gas to the inside, it's changing the outside pressure? So if I add gas to a balloon, immediately the atmospheric pressure goes up too? No. Okay, so this is what I was talking about, and I'll talk about it more in notes yesterday, is that when we add, here, let's say this is the outside of the balloon, one side of it. If we add particles, the pressure internal will go up, and the internal pressure will be higher than outside, and that will force the balloon to expand. Well, how far will the balloon expand? It will expand until the internal pressure is equal to the external pressure. So that's why I'm trying to get you guys to understand is that if the walls of the flexible container are not moving, internal pressure is equal to external pressure. If they are moving one way or the other, then those two pressures are temporarily unequal. All right, so what about number 15? What do we say for experiment D? I'll give you a hint. This part and this part are going to be the same in this answer. Okay? Add heat. Particles move faster, which we should know or be working on understanding that how fast the particles go is called average kinetic energy. So we're saying average kinetic energy is increasing, and then we'll take these two answers and add them to that, which means there will be more collisions. There will also be more force in these collisions, which will lead to a higher internal pressure, making the balloon expand. And it will expand until the internal pressure is then balanced with the external pressure again. Okay? What about 16? If we reduce the outside pressure, okay, if we reduce the external pressure, the balloon is going to expand, right? Why? Jerry? than the inside. So what I was just talking about the sides, the walls of the flexible container, is that temporarily the internal pressure will be higher than the outside. Okay, which means in terms of the particles, they're still moving around and hitting the sides of the container just as often as they were before. So the pressure inside isn't changing. But now the pressure on the outside that's hitting the balloon, the particles hitting the balloon on the outside, is becoming less. So again, the wall of the balloon is going to expand until when? Until the pressures are equal again, right? Okay, good stuff. Good stuff. And that's our stop sign, so we'll stop right there.